right, maybe we'll start. So it's a pleasure to introduce Alex Lubotzky from Weizmann and NYU. He's giving a lecture series at Northwestern this week, so we managed to lasso him in here. A day early while he's still jet lagged, so he wasn't strong enough to resist. So in any case, our aggression brings us today's speaker, and Alex will talk about his title. Okay.
Thank you very much. It's a real pleasure to be here once again. So many times in the 90s, even slightly less in the last decade, I really should work to repair this.
I'll talk to you in the car.
Anyway, I want to talk today on uniform stability of rank 1 of I-rank lattices. This is joint work with Lubotzky, Nicolas Monod, and w.r.t and Kazhdan. He's a student of mine and is now a postdoc in Belgium. So let's start with rigidity and stability and see the connection between them. I know that in this university is probably the world capital of rigidity, so probably the secretaries also know about rigidity, but because it's a colloquium, I will try to not to assume too much background. Let G be a semi-simple. We can assume simple for every question here is really the same. Simple Lie group over a local field. So it can be the real number, it can be the complex number, it could be also p-adic numbers and even characteristic, local characteristic P. Let gamma in G be back to back. Let gamma in G a lattice, so lattice means discrete subgroup of finite covolume. So the G mod gamma is finite G invariant measure. These lattices are divided to uniform, namely co-compact, which are always of finite covolume, but also they are non-uniform, namely not co-compact, which are still lattices. We denote the rank of G over K. So if you know what is it, fine. If you don't know, just think about SLN, and the rank of SLN is n minus 1. Now, it's kind of well known in the theory of lattices that there is usually, I want to stress, usually it's not always, the dichotomy is not always like that, but usually there is a difference between the case rank equal 1 and rank greater or equal 2. And we call rank greater or equal 2 I rank. It's not very high, but this is called I rank. For example, this related to properties like local rigidity, strong rigidity, super rigidity, congruent subgroup problem, and even something which I work on in because there is some logician here. There is something a first order rigidity of I rank lattices, which is against what happened in rank 1. So there is even many aspects, and a congruent subgroup property, for example, which asks whether every subgroup of finite index is a congruent subgroup. So SL2Z is negative solution, but SLNZ, remember, the rank is n minus 1. So SLNZ n greater or equal 3 is exactly the I rank case. Today we are going to talk about another property which usually goes under the name stability, and specifically today under the name Ulam stability. Some people call it uniform stability, and sometimes in order not to fight with any group, we call it U stability. So you can think of it as Ulam stability, uniform stability. This is the same thing. I want to warn you that this. Hi, good day.
Good to see you.
Good to see you. And this is And this is, so today it's about Ulam stability. I'll explain in a second what it means. But before that, what is usually a rigidity result? A rigidity result says the following. There is a clear, easy to understand family of representations of gamma. And the theorem said that if something is similar, it is already in the family. So like super-rigidity, the most famous results says that you take a lattice like SL3Z, you take a representation of it to any SLNR. There are two clear type of representations, the finite ones, and the one which induced from algebraic representations of SL3. And so these are the clear examples. And the super-rigidity says that every representation is one of these or some kind of a combination of them, tensor product or something like that. Now, Ulam stability is a statement like that, but for almost representation. So now let's say what we mean by almost representation and what we mean by stability or rigidity of that kind. Let gamma be a group. Doesn't have to be a lattice, can talk about any group, usually finitely gendered, finitely presented even, but doesn't matter. Let Gothic G be a family of groups, Gn and Dn, where Gn are subgroups, which we can specify later, and Dn is a bi-invariant metric of the group Gn. Now definition, gamma is uniform or Ulam stable with respect to this family. It's always a gamma with respect to a family. If for every epsilon greater than 0, there exists delta greater than 0, such that for every n, the important thing that it's uniform in n, and every map means map, not homomorphism. It's just a map from the group to G, which is almost homomorphism, namely dn of phi gh, comma phi g phi h, namely the distance between phi gh and phi of gh and phi g times phi h is less than delta for every g and h in delta. This will be today almost homomorphism. I will make a warning because the literature sometimes have other notions. Now, assume you have such an almost homomorphism. Okay, what is the clear example of almost homomorphisms? Take homomorphism and just, destroy it a little bit, move things a little bit, and then it will be almost homomorphism. So, the stability means, which is, if you want, the rigidity means that there exists indeed every such almost homomorphism. It's just a small deformation of a real homomorphism. There exists a true homomorphism psi from gamma to Gn, such that the distance between phi g and psi of g is less than epsilon for every g in gamma. To say in words, every almost representation is just a small deformation of a true representation. Okay, now the wording. Don't confuse with what is called in the literature usually stability or ordinary stability. They are similar but different. The easiest way to see the difference between the two definitions is the following. With ordinary stability is equivalent to the following statement. Now I will not do with epsilon delta. I will give both definitions in a different language. If phi n from gamma n is such that for every g in h, the distance of phi n gh and phi n g times phi n h goes to 0. This is the assumption, then there exists an homomorphism, true homomorphism, such that the distance between phi and g and psi and g goes to 0 with g for every g in gamma. This is the standard stability, the ordinary stability. Now, what's the difference? The uniform stability is really equivalent to the following statement. If phi n are any maps from gamma to gn such that the supremum over every g and h of the same distance goes to 0, okay, then there exists a true homomorphism such that the supremum over g of this distance go to 0. You see the difference. Here, the convergence to 0 is local. It's for every g and h. It's a different convergence, so here we assume less and we require less. Here we assume a stronger property, but we also require a much stronger conclusion. Okay, so you can see the literature both, and there is interest in both. There are some questions on one and the other. Today, I will say a few words to compare to ordinary stability, but I worked a lot on ordinary stability. I mean, I'm not trying to put it down. In fact, it's sometimes my favorite. But for today, I will talk about uniform stability. Now, we also today will work only with where Gn is just one set of groups, the unitary groups, Un. And Dn, we can take very rich, more or less take almost, not all, but almost what you want. So a Dn will be any matrix, choose your favorite matrix, provided it is induced by a sub-multiplicative norm. Namely, you have a norm on M and C, on all the n by n matrices. Sub-multiplicative means that A, B, the norm of A times B is less than the norm of A times the norm of B. Then the distance between A and B is simply the norm between A to B. There are many examples like that. For example, the operator norm is like that. The Frobenius norm, which is just a name for the standard L2 norm, is also like that. There is uncountably many norms like that which are not equivalent, and in some sense, every choice is a different story for us. They call the P-Schachter norm. The P-Schachter norm is like the LP, but it's kind of the LP of the eigenvalues. So the formal definition is you define maybe first the absolute value of a matrix is not A time A, it's like A conjugate. You take the A conjugate time A. You see, so such a matrix is always non-negative definite for every complex number. Then we can take the square root. This is called the absolute value of A. And the P-Schachten is you take the trace of A to the P, and then you take 1 over P outside. If you think about it, if A would be a diagonal matrix, this is like the LP norm. So these are the examples that we will treat. The non-example that unfortunately our method don't work for, and it will be very interesting to find, but a new idea is needed, even though it looks like just a technical difference, is the Hilbert-Schmidt norm. The Hilbert-Schmidt norm is nothing more than the L2 norm, but normalized. It's the trace of 1 over n a to the 2 half outside, or if you want, it's just the a2, the P-Schachten for P equal 2, which is just the same as the L2 norm, divided by 1 square root n. You think, what's the difference? It looks like the same, right? Who cares? But it's exactly the problem that the Frobenius norm is sub-multiplicative, but the Hilbert-Schmidt is not. And this little difference make a big difference for us. I don't know if this is the truth, but all our method breaks if we don't have sub-multiplicative.
Earlier you mentioned that you were taking Dn to be a biinvariant metric, but like, are there lots of choices for?
Yeah, the matrix is by invariant because by invariant by unitary matrices. I'm just looking at map to the unitary, and you just check that you say if you multiply by unitary matrix, either from the left or from the right, all these norms are preserved.
Yeah, makes sense.
So by the way, so each dn, I mean, I could mix and match.
You can mix in our theorem today. So
and I could consider like un for every value of p.
Yeah, take for un take
same n.
dn.
Yeah.
You can take the same p. You can take different. Right. Yeah, it's kind of interesting that it works. There are some. I could give a course on full course on ordinary stability, and then there are more things are more less clean somehow.
Is your gamma just a discrete group, or you have
Just discrete finitely generated?
For asking the questions.
Homomorphism, we don't care about topology.
Right. No, discrete. Yeah, we can, but it's difficult enough here. I like that. Okay. So here's the main theorem. Let G be UN, Dn, D sub-multiplicative. Gamma now a lattice inside a I-rank simple Lie group over a local field. Then gamma is Ulam stable provided G satisfy condition GQ1, Q2. The condition GQ1, Q2 is pretty ugly, so I push it to the end. I want to stress two things. First of all, that the condition is on G and not on gamma. Okay, hold on. We believe it's true always. We can prove it only if G is satisfied this ugly condition. Because of a technical reason. I tell you, I wish somebody young will go into say that, oh, you were crazy. You can just twist the argument and do it always. It might be the case. I'll explain what's the story in a second. But G, Q1, Q2 is really satisfied by most simple groups. For example, if K is non-Archimedean, cat is 0, it always satisfied. Is K is the complex number, then it always satisfied. For real groups, for groups over the reals, we can give you exactly the list when it's satisfied, when it's not satisfied. I stress, we believe the theorem is true always. But our method breaks because of some technicality if you don't have this G, Q1, Q2. Toward the end, we kind of prove most of the theorem except for the last 10%. We tried, we failed, and then we decided to publish it like that. Yeah.
Do you still require that gamma has finite covolume or not?
No.
That's
it's a lattice finite covolume, but it can be co-compact or non-uniform, both. You'll see the co-compact is actually, in some sense, this problem is even more difficult. But for SL and R, for example, as I said, both groups satisfy. So SLDR, it should be I rank. So we are talking about D greater equal 3. SLDR, if D greater equal 4, satisfy this crazy condition, but SL3 not. It's kind of frustrating, but what we can do. Okay. So this is a fairly general theorem, but not complete. We are not 100% happy, but that's what we can do. Okay. History of the whole subject of almost representation.
Is it obvious that in rank 1 this is meaningless?
Yeah. I think it's will appear one. Rank 1 lattices are never Ulam stability. Ulam stable. Yeah, that's a clean cut result. Not of us, it was or it's like putting, maybe not known explicitly in the literature, but was like putting two results in the literature which follows this immediately. I'll get to that. Okay. Kazhdan in 82 proved that amenable groups are strongly Ulam stable with respect to the operator norm. What does it mean strongly? They are they satisfy that every almost homomorphism is nearby a homomorphism, even for representation over infinite dimensional Hilbert space. Like in this lecture, I'm talking only about finite dimensional. For a reason, you'll see in a minute why.
And which norm, by the way?
What?
Which norm, right? You have sub-multiplicative norm.
Well, okay. Thank you for the question. Kazhdan proved it only for the operator norm. But our method shows, and in fact, if you go and check Kazhdan proof, but our method is kind of a
I would just
conceptual-
ask him, and then he'd say it's okay.
Yeah. Okay, so that in some sense, our proof gives also a conceptual explanation to Kazhdan results. In 2013, Burger-Ozawa-Thom started to look at this Ulam stability for general discrete group gamma. It's a very nice paper in the Israel Journal of Mathematics that year, and they prove, for example, the negative results in the following sense. If gamma is any discrete group containing a free non-abelian subgroup, which is like not amenable, namely in particular non-amenable, then gamma is not strongly Ulam stable. It's not strongly Ulam stable. The proof is not difficult. The proof is basically there is the results. So you see, you have to be a bit careful here. Free group, which are the easiest to handle for most questions, are not Ulam stable. If you digest the definition of ordinary stability, then free group are stable in the ordinary sense in a trivial way. Every map from the generators is a representation, so basically that's relief. But free group, that was a cute argument going back, I forgot whom, but they said, okay, but I want to give you the proof because in some sense it will come up in our proof. You start with the free group which is not stable, which means it has almost representation, which are not nearby representation. Then induce from that free group, take the induced representation. You ask me what is induced? I'm not taking induced representation. I'm taking induced almost representation. But if you know what is induced representation, then you can also define for yourself what does it mean induced almost representation. And that induced almost representation is not nearby a true representation. So if you contain, you are not strongly. But it leaves open to be Ulam stable. And that's exactly what we prove. I really wrote it because I want to popularize this open problem, which is really, I think it's an outstanding problem, and somehow some of my students and maybe some other people try to solve it so far with no success. You know, amenability is a good number of characterizations. Now look what we have here. Kazhdan proved that amenable group are strongly Ulam stable. We know that if a group contains a free group, then it's not strongly Ulam stable. The natural question is whether every non-amenable group is not strongly Ulam stable. You know, this was a long tradition about amenability. At the beginning, people thought that every group without a free subgroup is amenable. This is by now known to be not true. There are various other questions like that. So this is a question which seems to be less known, but I think it's a kind of a little beautiful questions and okay.
Professor? So for like SL2 contains a free non-abelian.
Sorry?
SL2.
But like But like SLN for n bigger than 2, does that not run?
They are not strongly Ulam stable.
This
In a
allows
minute, I'll
infinite
show you
dimensional
that they are
Sorry.
Ulam stable. Strongly means also with respect to infinite dimension. The point is that if you take a free subgroup of infinity index and you take this induce of the almost representation, you are getting an infinite dimensional representation, which is almost representation, not nearby. So you are not strongly stable, you can still be stable. And in fact,
Thank you.
Burgers, Ozawa and Thom showed that there are nice groups which are, let me give you two results of them in that paper. First of all, they showed that if the map from H to bounded cohomology of gamma to R to the H2 of the ordinary cohomology of gamma is not injective, then gamma does not have Ulam stability. For the expert, I would say that people who, what is, I hope people know what's cohomology. What is bounded cohomology? Bounded cohomology means that that the chain are bounded. Now, you have to be a bit careful. So cocycle, why there is a map from bounded cohomology to ordinary cohomology? Because if something bounded is a cocycle, then it's also you take a cocycle, bounded cocycle, then you map it to the ordinary. It's also cocycle, but you have to be careful. It might be that even if the image there is trivial, meaning that this cocycle is a co-boundary of something, is not necessarily a co-boundary of a bounded cochain. Okay, so you have to be careful. So this map from H2 bounded to H2 is in general neither injective nor surjective. There are various theorems that sometimes it is, but for example, it's known that for hyperbolic group and more generally for lattices, all lattices in rank 1 Lie groups, this map is not injective.
Just to clarify, so a bounded cochain is one in which there exists some constant so that the values, the evaluation on any chain is less than that constant? Okay, I see. Okay.
Exactly. This became a big subject. I think it was invented by Gromov, right? Like everything. And became very...
Based on idea of the Thurston.
What?
It's based on idea of the Thurston.
Okay.
Anyway. So by the way, and is this failure even based on maps into U1?
Yes. Very good. Yeah, it's even, in fact, what is known that this kernel is exactly give you almost to R, and then you take exponential map from R to the circle, and that's basically it's not difficult. All this is not difficult. But more interesting is that Burger-Ozawa and Thom in the same paper proved that SLD-Z. In fact, they prove it also for SLD-OS or for every ring of algebraic integers localized at finitely many primes, they are Ulam stable. But the proof is not difficult, but it used in an essential way a property called bounded generation of the group SLNZ. Bounded generation means that there exist finitely many cyclic groups such that the product of them, just the set, that the product of them, not the group generated by them, the product of them is the full group. It's an odd result that SLD-Z are bounded generation. It's an old conjecture that all non-uniform lattices in simple Lie group are, at least over R, not in characteristic P, of course, and are a bounded general, but it's far from being proved. But for us, more relevant is the quite recent results in the last couple of years, which was really a big surprise against many expectations of many people, me included, is the results of Vaja, Rapinchuk, Ren, and Sanier, who showed that co-compact lattices are never boundedly generated, which means that the method of Burger and Ozawa is very limited. As I said, for non-uniform, it is at least conjecture that they are boundedly generated, still far from being proved. But for co-compact, they are never. So there is no way to start. Okay. Now I want to recall something about the bounded cohomology. It's a well-known result that if gamma is amenable, then all the bounded cohomology vanish.
What is V here?
What?
What is V?
B means bounded.
Everything.
Yeah, V,
Oh.
coefficients.
Any module.
Any module, yeah.
Any module.
Finite-dimensional.
I think even this is even for infinite one, and it's not a difficult result. You can kind of integrate in order to find, because you can integrate on a bounded function on a amenable group, then you can kind of solve and find the solution to. A deeper result, which was proved by a number of people, in partial, some general, is that the bounded cohomology of a I-rank lattice is 0 for every n if gamma is an I-rank lattice, provided the V gamma, the set of fixed point is 0. If you take representation with no trivial sub-representation, with no vector which is fixed by all the element, then the cohomology, the bound cohomology vanish for these lattices. This was proved by Burger and Monod for n equal 2, by Burger and Shalom for n equal 2, and some for more general V I will not explain, but with a very different proof, but in a sense, this is important for us, so that's why I mention it. And then Monod proved it for every n. Now, Monod noticed the following, and in his ICM talk in 2000, he asked, look, the bounded cohomology vanished for amenable. The bounded cohomology H2 vanished for I-rank lattices. He already knew somehow about, even though it's before, about the Burger-Ozawa. That he said, is there a connection between Ulam stability and bounded cohomology? So the answer is yes, but. I'll explain where the yes come from almost immediately, and then you see, oh, we are in trouble here, and we'll get to that in a second. Before we go to that, I still want to say something about stability and second cohomology. And now for a minute, just for the next two slides, I'm going to talk about stability in the ordinary sense. Because this thing that I'm going to tell you here about stability in the ordinary sense motivated us to go to study uniform stability. Because there we really had a connection between stability and vanishing of H2. So there has been really a lot of quiet progress in ordinary stability in recent years. The major, I think it's fair to say that the major technical tool to prove stability is the following. Now, let n be the natural number let U be an ultra filter on N, so the logician can tell you if you don't know what's ultra filter. If you don't know, you can manage to go with me ahead, even if you don't know.
You can say weak star limit.
Yeah, right. So I want to talk in.
So simple.
I want to talk in that. I'll explain everything. Now let Ln be the Lie group of Un. So the Lie group of Un is really matrices, some matrices in M in the n by n matrices. I take the same norm as above, as before. Fix the norm, whatever you want. Shmuel, you wanted to take for every n a different one, whatever. Now let L be the ultra product, the topological ultra product of this Ln. If you don't know, what is ultra product? It's more or less, think about it in the following way. You take the direct product of everything, of the old Lie algebra, and you divide it by the normal subgroups of all the sequences which converge to 0 when n goes to infinity. Okay? Now here is a trick which is very useful in this story of almost representation. One of the difficulties to work with almost representation, that we do group theory by now for what? At least 200 years, if not more. And homomorphism as a kernel, homomorphism as an image. I studied what is almost homomorphism. What is the kernel of an almost? That can always change a little bit. What is the image of almost homomorphism? So the trick is the following. You take a sequence of almost homomorphism. Don't look at that. Look at me for a second. You take a sequence of almost homomorphisms. So if you have such a sequence of almost homomorphism to, you see, phi n from gamma to Gn, then you can get one map from gamma to the product of the Gn, just a diagonal map. This is not homomorphism, but if you divide it by the sequence we convert to 0, or in the professional language with the ultra printer, then suddenly these are homomorphisms, right? Because what is the meaning of this to be almost homomorphism? It exactly means, remember this slide which says that if you go to infinity, the distance between phi gh and phi g phi h is getting smaller and smaller, which means that the distance is exactly in the kernel. So suddenly you got a map from here. The situation is even more interesting. I already give you an hint to what will come up. So we have the product, and the product is going to here. If you think about here for a second, and this is now homomorphism. You see, before that, this one was not homomorphism. Stability is equivalent to the fact that I can pull back phi to a map from gamma, which is the full back of this one. This is phi now, which is a true homomorphism. If you think about it for a second, you see that's exactly that, because you pull back to something which is equivalent to homomorphism, which is equivalent up to these sequences which converge to their identity. Right? So stability is a lifting problem. Now, what is the mathematical tool to work with lifting problem? H2. But H2 with coefficients in a billion modules. That we know to do very well. But here the kernel from here to here is so far from being a billion. Just think about it. These are all the sequences of matrices which converge to, like in UN, which converge to 0. It's not a closed subgroup. It's terrible subgroup. It's a dense subgroup, in fact. So this is a terrible space. So somehow we cannot do right away. What we proved, and that's the major breakthrough of this theorem in a previous paper of the Schifre, Glebsky, Andrea, Thom, and mine, we proved that the almost homomorphism phi n in the standard sense, first of all, almost homomorphisms give you a homomorphism to the ultra product of the UN. The ultra product of the UN acts on the ultra product of the Lie algebras. So we are really getting an action on this Lie algebra. If H2 of this action is 0, then it is close to homomorphism. Why we could do it? I just told you that our kernel is very far from being a billion. True. But because of this little property of sub-multiplicative, we could prove that you can do little steps, that each one of them is a billion. The kernel is very non-abelian, but somehow it has a billion by a billion by a billion, and we do the extensions, a vanishing of the cohomology, and show you that you could do extension each time in a small step. And then basically you take the limit and you get an extension. But we need a sub-multiplicative. Without this, it doesn't work. That's why for L2, for the Frobenius norm, it works. But for the Hilbert-Schmidt, when we normalize with 1 over square root of n, it's not sub-multiplicative. Our method completely failed. Okay, so this is the reason. So okay, what happens there? Not only that you get, so you see, the ultra product now is an Hilbert space and blah blah, and then you get. Okay, so this is another paper. Our work on the unitary came by the following observation. You see that Glebsky and me were also co-authors here, and we said to ourselves, if we study, you have to concentrate on that, maybe you're too tired this time of the day, and then you get that the co-cycle which appear here, blah, 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 are bounded. So if we want to prove the same theorem for uniform stability, the co-cycle are bounded, great. What we need? Vanishing of the bounded cohomology. And we have the theorem of monod and monod shalom, etc., and showing us that for I rank, we can do it. Wonderful. We will answer monad quotient. He asked if you can do connection. Yes, of course. We will imitate this proof. And then we saw that we have a very delicate gap. So here I explain, which I already told you, what H2 has to do with the subject. So really, what we need is to take this homomorphism and lift it to an homomorphism. The kernel is very non-commutative, but we can approximate it by small steps. Okay, I already told you all this. Okay. But we wanted to apply, and we just finished the paper after 10 pages in the bound community. But there is a very, very delicate issue, which those who are not used to or don't know what is ultra product can miss it, and this includes me till after realize the mistake. What we get here in this ultra product is co-chain are what is called in the non-standard analysis internal maps, and we have to take cocycles which are internal and to fill them by coboundaries which are internal. Now I'll explain in a minute what does it really mean. And I don't want to stop for that, but this problem does not appear in the ordinary stability, because the ordinary stability, the whole notion of stability can define only on the finitely many generators. And if you have only finitely many, it's not a problem. So I don't want to stop. I mean, it's really just going over the definition, and you can see. Take my word that there is a delicate issue here that we are using. So, I will put it into a very concrete word. What we need is the lifting problem of the following kind. So the gamma group is Ulam G stable if and only if for every homomorphism that has an internal lift. You see, not every, or if you will start with an homomorphism from ear to ear, you don't necessarily can lift it even to a map to the product of UN. You see, in which factor like different product. Because you see, I misled you because I talked about this. You have to take also here the ultra product of gamma. I forgot to miss it. Okay, but I can explain now in simple word. You see, we start. You remember this phi, which is homomorphism from ear to ear, really came from a diagonal map to ear. So I have to care only about homomorphism like that. So I have to care about less homomorphism. This is kind of the internal one, and I have to. But when I lift them up, I have to lift them to internal maps. So the gamma star, you can think of it also as a product of gamma with itself infinitely many times. But I need that the maps will be those which are go like one to every event. I feel that I did a bad job on that, but it's really, believe me, it's just going. There's nothing deeper. But it's just so that the bounded cohomology is not quite the right tool. In fact, this led us to capture this problem, we define a new cohomology. We call it the asymptotic cohomology. This is the asymptotic cohomology of gamma acting on this Lie algebra. In fact, it's really not gamma that acts, it's gamma star, which I forgot to say, which deal only with internal cochain. So the story is like that. I explained at the very beginning that there is a map from the bounded cohomology, B down, to the standard cohomology, which is neither injective nor surjective. In a similar way, there is a map. Maybe let me show. There is a map from our new cohomology, the asymptotic cohomology, to the bounded cohomology, that in general we have no idea whether it is injective or surjective. But to prove stability, what we need is vanishing of this new cohomology, the asymptotic cohomology, and not of the bounded cohomology. Okay, so here is the main technical theorem. If this asymptotic cohomology vanish, again with respect to blah 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 blah, then the phi n are nearby to homomorphism psi n. Now, as I told you before, the theorem the theorem of vanishing of cohomology, the theorem which says that the bounded cohomology vanishes for amenable group, is not a difficult one. And you can imitate this line by line to prove that the asymptotic cohomology vanish for amenable group, and therefore you can deduce Kazhdan theorem. You remember Kazhdan told us that amenable groups are. So that's kind of giving you a little more conceptual proof, but it's basically the proof of Kazhdan. Okay, now in the last few minutes which I have, I will have to share with you this, just to give you, you see, this turns out instead of being a 10 pages paper to 80. Because you will see that every, and in some sense it's a paper which tried to copy the proof of Monod Shalom. You remember Monod Shalom proved that H2 bounded cohomology vanish for I-rank lattices. What we want is to prove the same result for asymptotic cohomology. We took their proof, of course, as you could see, we hire Monod into our team. Yeah.
Sorry, question about the Sorry, I had a question about the previous part. But, wait, so Kazhdan's result proves strong Ulam stability, right? Kazhdan's result.
Oh yeah,
gives you
so good. Yeah. This proves it only for the finite-dimensional formally, not for infinite-dimensional. But I think if you really want, you can do it for the infinite the same way. It's not. I mean, I never checked that, but I think it's not. It's from this point of view, somehow the Kazhdan theorem is getting conceptually clearer. Though Kazhdan had this idea in mind, if you go to his paper, you see he kind of worked with approximate cocycle and approximate boundaries, and so he didn't formalize it as we are doing it using ultra product, etc. He did it like step by step somehow. It's basically okay. Now, let me recall, so I just want to start to show you the proof and basically not really to give you the full proof. I want to show you why things which are standard in the ordinary category suddenly become complicated. Though, I have to admit, my friend, I stress still my friend, and my colleague Uri Bader, when he saw that, told me, you surely don't have the right proof for the theorem. Because suddenly everything become more complicated, and he said, there must be a cleaner proof. Anyway, that's what we have. Okay, let me start with something that, you see, you remember that I stressed that the theorem eventually, if we succeed to prove the theorem, then if we succeed to prove it to all the lattices in a simple group G. Right? Doesn't matter what is the lattice, it's only matter for us who is the simple group G. Why? Because the first step of the proof is the so-called Shapiro lemma. Shapiro lemma is the standard lemma that I guess in graduate courses you learn it at least for finite groups. You have a representation of a subgroup. You induce the representation to the group, and the cohomology is preserved. Now there are a million different Shapiro lemma, Ekman-Shapiro lemma in other contexts, and each one becomes a little bit more complicated. Here it became really more complicated. Why? What we wanted to imitate? We wanted to imitate the above theorem. This theorem is not that complicated. It's still in the standard world. If gamma is a I-rank lattice in G, then for every dual Banach space, so it's some Banach space, that doesn't matter, with gamma action, if we take V to be gamma module, we induce from gamma to G, and we get W, then the cohomology is the same. And also the bounded cohomology is the same. Okay? That's a standard theorem. And the proof is more or less like the classical. Now, we managed to do it, but really with a lot of work. Why a lot of work? You see, so we proved what we want to drive. We proved that the asymptotic. You remember we had this Lie algebra. We had the cohomology of gamma in L, but this notation is kind of misleading a bit. It's not really the cohomology of gamma. I write it as a cohomology of gamma, but it's really the cohomology of the ultra power of gamma acting on the ultra power of the Lie algebras. And this is the same as the asymptotic cohomology of the ultra power of G acting on the induced model. We have to explain what is even the induced model. Even this is not clear. Because, as I say, this is not really, we write it as G, but it's really not G. Really, it's G star. It's the ultra product. So, you see, the standard proof of Shapiro lemma, what does it mean? How do you do it for gamma star inside G star? For example, gamma is a lattice in G. But what does it mean? Is gamma star a lattice in G star? Actually, I believe that maybe you, the logician, can help us here. Because maybe there is a theory that we don't know and should be developed to show that if you take gamma a lattice in G, then you can get some kind of generalized, you see, this is not compact anymore, it's not finite volume in the standard sense. But maybe in some kind of a non-standard sense, non-standard analysis, one can make here a measure and then the proof will work. If you even think, you see that it's not so clear, what does it mean, the L infinity? What does it mean, the L2 in this sense? So we have to work out every such little lemma, 2 weeks, if not more. Sometimes we're stuck on something, and then till we manage to get it and eventually prove it. But you see, these are the kind of difficulties that you work out of the usual categories. There is no R measure anymore, etc. Now, in the monod shalom proof, as I said, we are imitating there. They prove that the bounded now, so we are in G at least. You remember, there is no gamma anymore. In the monod shalom proof, they prove that if you have a G acting on such a Banach space, then the bounded cohomology is equal to the bounded cohomology of the fixed point set. So you see, if there is no fixed point, everything is great, everything works, and okay. Okay. Now, we managed to do it. But we managed to do it in the following sets. So the corollary is, if there are no fixed point, then it vanishes. Well, we need to say the following. Assume W has no fixed point up to infinitesimal. Namely, it's kind of a stronger property, not only not fixed point. There might be points which are almost fixed, and they can cause trouble. If you don't have them, you can do it. So this goes and goes for 80 pages. I hope that even in a seminar talk, I will not dare to bring you all this nasty work. And certainly not in ecology. I just want to show you the kind of difficulties that you start to imitate a known proof for bound cohomology in the new asymptotic cohomology. Maybe the right thing to do next is to study the asymptotic cohomology for its own sake and formalize it better than what we did, and axiomatize some of the properties, and then things will be smoother. And then you have to go to deal with the fixed point. And this fixed point really what causes us to have this strange property. If we had the strange property, we could handle this fixed point with infinitesimal. And I cannot really even explain why this was like that, but I just tell you just to see how ugly it is. That's why I pushed it for the last slides. Otherwise, you all will get out from the room after the first or second slide. This, but I own you this, I'll take it, and now you cannot escape. This ugly condition G, Q1, Q2 mean that G has two parabolic subgroups, Q1 and Q2, satisfying that their intersection contains a minimal parabolic subgroup, and together they generate the group. The H2 bounded cohomology of them is 0. Now you see the problem here with SL. You remember that SL3R it doesn't work because in SL3R the two maximal parabolic subgroup are extension of SL2R modulo amenable, and therefore the bounded cohomology of them is the bounded cohomology of SL2, and SL2 it doesn't vanish. You see, so this is the catch with SL2, but with SL4 there is no problem. And we also need that H3 is ours. So this is something that you can be optimistic. Because this is kind of, I think maybe the people in the you see, this is about bounded cohomology, and the people working on bounded cohomology, I think that they believe that this always happens, unless this, which is not it's not true. Anyway, most groups you just go over the list of whether the two properties exist or the known literature. As I said, most simple groups are proven, but still the story is not complete. A lot of young people here who are invited to delve into it and to show us they can do it so much better. Thank you very much.
How different is this bounded cohomology from like the notion of like parabolic cohomology? For SLN or something?
Now, what is parabolic cohomology?
I think it's like
it's a cohomology with
like
with respect to the parabolic. I forgot.
Like you look at the cusps and then you want classes that like vanish
Right.
on the, or
that vanish over the cusps. Right. I don't see.
because these are like in some settings these look like these end up being like
right,
bounded.
because you mean they go to 0 along the cusp. That's what you need.
And so it's like if you look at the
I don't know.
compacting,
It's interesting. Might be. I don't know. It might be that.
They're really different.
What?
they're really
They're
different.
really different.
Very different. Shmuel knows everything. Busted.
I can opine about anything.
So this you were talking about this notion of almost homomorphisms, and sort of made me think about this. This is like a coarse geometry, like a study of groups, right?
Right.
And, like you like quasi-isomorphisms and quasi-isometries and so on.
Maybe what one need is a unified theory. There is, and it's kind of related also to this notion of approximate subgroups, that people like Hrushevsky and Terry Tao promoted, which are, this is kind of, the whole subject is starting almost, whether almost is really nearby a true. Usually you say it for children if it looks like a zebra, if it's, talk like a zebra, then maybe it's not a zebra, but it's nearby a zebra. That's the message. You see, so in the course, course rigidity, I didn't mention the first, I had to remember it was done here by Benson and Eskin, right? So it's kind of the course rigidity is, if you think about it, is a similar style. You take two lattices, you take a map between them, and the usual map are the homomorphisms, and the course tell you that if you have a course map, that it's nearby a true homomorphism, right? And Margulis and Mosto will tell you that such homomorphism can be algebraic homomorphism. So every step is pushing farther and farther. We pushed here to another corner of almost a unitary group. I don't see, but I will not be shocked if in 10 years somebody will give kind of a unified approach to both of them. It will be wonderful because it will show that there is now a lot of interest. It's little bit, if you come to my lectures in Northwestern, and then you see that all this attitude, a little bit influenced by computer science, question of testability in computer science.
Property testing, obviously.
Property testing. And property testing is something of that kind. You check locally a little bit. It looks like it's okay. Then you want to deduce that it's nearby. It cannot be. You take a error corrected code. You take a long word. You don't read it all. You read only part of it, small part of it. It looks like it should be in the code. Then maybe there are mistakes. Maybe it's not in the code in some other places, but the probability testing that it's nearby. So it's the same style.
Actually, it's not only the style. The first results in property testing were precisely this. Only right as very primitive people we consider Hamming distance.
Right. You're right. No. I mean, I'm one of them. You take the Hamming distance on the symmetric group. That's bring you to the notion of Sophic, etc. But to hear about all this, you will have to go either to Northwestern or to invite me once again.
So maybe we should thank the speaker.